Okay, so first of all, I want to thank the organizers for coming up with this great idea and let me be part of it. Yeah, so I'm going to talk today. It's about dynamics in open quantum systems. I did some years ago, I did some work on using unravelings of Markovian systems to follow the dynamics of entanglement. And then I was always wondering how to do this for non-Markovian unravelings, and then I got into a different business. One of them was quantum thermodynamics, in which approaching the stuff from quantum fluctuations, you can use also Markovian trajectories, and I was wondering how to do this for non-Markovian case. And then, yeah, I had some discussions with Walter, and he got his chemo just arrived there, and he got interested on this, and so we found a way to extend the set of non-Markovian stochastic equations, those Schrodinger stochastic equations, and yeah, and then, well, okay, remembering how this works for in the case of Markovian case for entanglement, we use this as a one application for it. So this is what I want to show you today. So, okay, everybody or many people have talked about entanglement in the last days, and they always say about talking about it like it's a resource, but then the point here is that it's also very fragile, okay? And so there is this idea of how to quantify it, and then there was this dream 10 years ago or something, how to get these dynamics, and how to go from to get an equation that will give you the evolution of entanglement from one point to another point, without going with the evolution of the state itself. Yeah, the reason is that this part here is usually computationally expensive, and the reason for this, which is that you have mixed states, as we all know, and then you cannot use average over the pure state decomposition of your mixed state. You cannot do the average for entanglement measures. You actually have to use a convex rule. And well, what we attempted at the time with Markovian equations was to kind of find an optimal decomposition here using the dynamics as the inducer of this decomposition into pure states. And kind of, if we cannot follow the exact way, well, just find very tight upper bounds or very good approximations. So I'm going to talk in the first part a little bit about how this works, because I think it's a nice way to approach the problem, and then in the second part I will show the case of non-Markovianity, which is what is interesting nowadays. So usually when you have a system which you're interested to look at it, and you have the environment coupled to it, well, you're losing information, and if you're working in the case of which interaction leads to Markovian evolution, in this kind of description, you will have a master equation for it, and then you will be looking at the evolution of rho. Yeah. You can, however, approach this problem in a different way, and is that you can make measurements on the environment. You can put a detector there, and then you can continuously measure what the environment is doing, and you can collect the result all the time, continuously. Then if you do this, you can follow the dynamics of the system, but now it's not going to be a deterministic equation like this master equation I just showed you. It's going to be an stochastic evolution. Yeah, so you will remain the system of your state. Sorry, the other way around. The state of your system is going to evolve stochastically, and what you will have is this kind of equation in which you have a deterministic part and then a stochastic part, and this state that you're getting here at each step will be a conditional state, and it will be conditioned on the result of the measurement that you're registering here. Yeah. So the idea there is that so you have this equation is nonlinear. You have this way for the deterministic part, in which this J just tells you about the coupling between the system and the environment, and this part here gives you the amplitude of the stochastic term, and this term here is just a noise that comes from the measurement, and this noise is you will usually take it to be white. And when this theory just first came around the 90s of the last century, people were just looking at one kind of unravelings here. These are diffusive unravelings, in which they have this correlation function of the noise here equal to 0. But just when the century turned, Howard Weizmann, he showed that actually you can put here a matrix for this noise and make it correlated here, not on time, but with different components. And associated with this choice of U here, you can select different ways of measuring the environment. So the dynamics, the conditional dynamics that you will have now will depend on how you measuring the environment. So not all ways of measuring the environment gives you the same conditional evolution. So you have here the currents. This is actually what you measure. And depending on the selection that you make of these U's, you can measure this in a different way, and then you will have different ensembles of trajectories. Okay? And so if you have different ensemble of trajectories, now you can think about how the entanglement is going to evolve along each one of these trajectories. And then if you do this, of course, I mean, we did this first for 2 qubits. You will have a conditional evolution of concurrence, which is also a stochastic variable now. And you can actually look for the average concurrence over the ensemble of trajectories that you have. Okay? And then hopefully you can look for ways to make this average concurrence to have something to do with the concurrence of the mixed state that is lying below. So the parameter that we now have free for doing this is this correlation matrix U. We finished and we put all this together a couple of years ago in this paper. And then the idea is, I mean, we work with these 2 measures, but actually we show that you can do with actually any measure if you want. And then the idea is, instead of doing this optimization here among all possible decompositions that you have of your density matrix, you can restrict yourself to the compositions induced by the dynamics and then make an optimization over these U's. Okay? And this is what every choice of this U will give you a different unraveling, and then eventually you can go to the lab and pick a different way to measure your environment, and you can optimize over this way of measuring, and you can put some type bonds to your entanglement evolution in time. So we did this some time ago, and it works quite well. I mean, you can look at it in this place, but everything here was for the Markovian case. Okay, and I always wanted to look at this in the non-Markovian case, but at the time when we finished this a few years ago, there was only one unraveling in the non-Markovian case. Okay, which has this, let's say the state of the art was like previously with the Markovian case before Weizmann work, in which this U was always taken to be equal to 0. People were discussing, I mean, we were discussing a lot how to do this, and finally last year we found a way to do it, which is what I'm going to show you to you now. So now I want to derive, I mean, I will not go into details, but show you the main steps to derive an stochastic equation for non-Markovian dynamics, and then I want to apply this to entanglement. Okay. So okay, we start with the usual setup, which is you have a Hamiltonian, which you have a system, a BAT, and their interaction. It's very important for us that the BAT is going to be a bosonic BAT, and then we have this kind of linear coupling here, and else are just arbitrary coupling operators acting on the system, and these are the B's are the bosonic, and G is the coupling amplitude. Okay, so the initial point is the Schrodinger equation for the whole system and BAT system. And the main step that we did here is that usually, I mean, if you look into the literature from the 90s up to here, one way to get this Schrodinger, this non-Markovian stochastic Schrodinger equation is that you will choose a basis for the environment, okay? And usually this basis is going to be a basis of coherent states. And what we realize is that we can do the job if we now use a squeezed coherent state. So now we have 2 parameters. We have the C, which labels our coherent state, And we have a key which gives us the squeeze parameter of this thing. And this stuff is complete, yeah, in the environment. So this means that this total state of the total system, you can write in this basis in this way, where here you have a Gaussian weight, and this stuff that appears here, this is the conditional state of the system, provided that the environment is in this squeeze coherent state, yeah? Which is the reminiscence that you have from the other kind of quantum trajectories for Markovian systems. So with this approach, well, it's the way we work. There is still one big difference I want to make a point here is that one of the nicest things that the Markovian approach has is that, like I told you, associated with the different unravelings, there are ways to measure stuff in the lab. Okay, it is not so for the non-Markovian case. So there is a lot. I mean, you can check every 2 or 3 years. There is some guy or some people claiming this, and then Howard Wiesemann, claiming that you can associate continuous measurement on the lab to this kind of trajectories, and then Howard Wiesemann will publish a couple of months later a paper showing that they are not right. Yeah. So, but in our case, what we are claiming is that you cannot do a continuous measurement on the environment, but you can do a single shot measurement. So like you can prepare your state, you can leave the system evolving time, and at certain time that you're interested in, you measure the environment, just a single time, yeah? And then you can get results from there, and this is what I'm going to show you. Anyway, so of course, when you're doing this with the conditional states, you want to be sure that if you average over all your trajectories, you recover the density matrix of the unconditional evolution, yeah? And this means taking this projector over the state of the system and tracing over the environment, which give you this. And this is a different form, if you see, to just make an average over the conditional states with the Gaussian weight that you need. Okay, so this part is satisfied. And the point I want to call attention here is that now we have this new parameter, which is the squeezing, and this allows us to select the squeezing of our bases as we wish, and this will be our unraveling parameter. So okay, so now what you do is you take this way of writing the equation, you put it here in your Schrodinger equation, and then you can get a stochastic equation just for the state of the system, yeah? So you throw away the path, and you ended up with this linear stochastic equation for the system. So here you have the state of the system. It is evolving. This part here is going to be the deterministic part of your evolution, where you have your the Hamiltonian of your system. Here you have an stochastic part. This C is going to be the noise. And here you have, because you are working with non-Markovian stochastic equation, here you will have a memory kernel that gives you the evolution of the system. Okay, so now you see there's an integral over time, and here you have a functional derivative, which is sometimes a bit messy. And this equation, like it stands there, is very, it's completely general. You can use it for any system. Of course, this is non-Markovian, so most of the time these results are formal, so this is a formal result. If you want to work system by system, you get into troubles here with this kernel, as the usual troubles, but you can still find cases in which you can work with it. So the main important thing here, and that was the main contribution that we did to the non-Markovian stochastic equations studies, is that we identified this equation, and we were able to get these correlations for the noises. So you will have here a Gaussian color noise now, in which you have mean equals 0, and you have these correlations for the noise. So like I said before, the work before us, they always were taking this correlation here equal to 0, and now we have it equal to some function that depends on, depends on 2 times, and it depends also in our unraveling parameter. So we now can play with these correlations. Okay, so this actually was the main contribution of the paper, and now we wanted to apply, this is just calling the Unravelings, we want to apply this on entanglement. Yeah, so that was one of the possible things that we had in mind. The other one is going into some other direction in quantum thermodynamics. So how we're going to apply this is we can look into multipartite entanglement, and we want to do to monitor the dynamics of this multipartite entanglement. So for this kind of dynamics, it's good to look into certain special cases of entanglement measures, which are called SL invariants. Okay, so these are measures that if you apply this kind of transformation to the state, the entanglement will not change. And these transformations consist simply of the direct product of local d by d matrices with determinant 1. Okay? And examples of this kind of measurements are the concurrence, the G concurrence, the tritangle, which are the most famous ones. And the main properties of these measures are, okay, first of all, is the invariance that I just told you. If you take an element of this group, the entanglement is not going to change. Then you have homogeneity, which just tell you that the entanglement, if you multiply your state by a real number, you just get the real number times the entanglement of your initial state. Finally, you can extend this to mixed states with a convex rule. So this is very convenient because this property here in which you have the invariance over matrices with determinant 1. And then what it is, then with this kind of dynamics that we were showing, you can apply this directly. So one solution, a formal solution of the stochastic equation that I just showed you will have this form here, where this time evolution operator is not unitary. And if you take this time evolution operator to come from a system in which you have each one of the parts of your system coupled to local bats, yeah, you can have that the dynamics, this operator here factorizes into local operators that act on each one of the subsystems, which satisfies, meaning you can show that it belongs to the SL group, this operator here. This is just time ordering, which you have to be careful. And of course, one big restriction, of course, is that the system Hamiltonian, the subparts don't interact among themselves. So the Hamiltonian is also local. So if you do this in a previous work, a couple of years ago, we were able to show that the entanglement of the system will follow this scaling function here, which I will not enter in the details. You have to kind of solve this operator to get this scale function. But the point is, you get a scale function which tells you that for all kind of measures that you have in the system, sorry, I made a mistake here. I put a G, this is just the same invariant measure here. You have the same behavior for all the states, yeah. And well, okay, then now you can use the convex property to show that if you average over this, you can find you can find an upper bound for the behavior of your entanglement. This is actually the rate between the entanglement of the state at some time t when you started with this state at time 0. So this was cool because we have the mean entanglement of the decomposition, and we can play with this parameter just to make this bound as tight as we wish, as we can actually. And so we apply this for a simple system. For non-Markovian dynamics, it's hard to find exact examples of states which, of problems which have been solved for all states under non-Markovian dynamics, but we found some. So actually here I'm putting 2 qubits, but actually you can put here many qubits in which only one of them is coupled to an environment. This is the case that we look at, just the first one. And the environment here is a dephasing environment, okay? So with the unravelings that we had before our work, some people have done the work already, and they have bounded entanglement dynamics in this kind of system with this red dashed line. And these are, I mean, we introduce the non-Markovianity in our system with the spectrum of the BAT. And then we consider Markov omic case and the super omic. So this one is the Markovian case, this is the omic, and this is the super omic case. And we were able to find a parameter that optimizes our dynamics, which is the blue line, and it actually coincides with the exact dynamics of the system for this particular case. Okay? So, and then the other thing that I can tell you, but there's no point in showing, you can actually protect entanglement with certain environments, with certain local unravelings. In that case, what you will have is that the entanglement never decays. It's just a line that remains here. Yeah, and with that, that's all I want to tell you. So what I think I have shown is, in a very succinct way, that diffusive quantum trajectories shows a complete and efficient method for characterizing entanglement for in the Markovian and non-Markovian case in multipartite system. You can, I mean, I just mentioned it, you can also protect entanglement with these unravelings. And what we're looking in the future eventually is to look into finite detection for experimental setup, yeah, applications to some experimental relevant cases. Yeah, thank you.
Questions?
To consider finite detection efficiency, are you going to have to move to stochastic master equations, or are you going to get to keep the Schrödinger equation?
No, we have to move to, but it's just a simple step to do that. It's very similar to the Markovian case, just to get a master equation in that way. Mm-hmm.
Other questions?
When you're doing the calculations, can you just, if you are, I don't know, just trying to simulate the dynamics, then you can just use the quantum trajectories in the same way that you do when you have Markovian dynamics? Like the Unravelings, you use it. I'm just worried about really the numerics. Like, were you doing this numerically or?
Well, actually, it's more involved because you have this part here in which you have the kernel evolution. I mean, to tell you exactly the truth, we work with cases in which we didn't have to do the numerics because we know it's quite involved, and we just wanted
possible.
to. Nina, which is the first author of this thing, she works on the numerics on this and applications to other problems. Yeah.
Okay.
But for the examples and just to put out the results, we choose something that we can calculate analytically and have control on everything and look for exact results that we could compare with.
Mm-hmm.
Mm-hmm.
Okay.
But yeah, okay, this, I mean, Walter's group, they have been working with these kind of equations, of course, without these unravelings, with the other one, which we call the standard, for many years, and numerics can be done.
Okay.
They are a little bit more involved, depending on your environment, because you need to solve this problem here.
Okay.
Mm-hmm.
Other questions?
Carlos, I got confused with the idea of the one-shot measurements in the environment, because usually for the trajectories you really monitor and
yeah. So yeah, this is a tricky thing. So like I said, I mean, there is in this community the big names are always discussing about this thing. So the example I was telling you is really true. So Yossi is convinced that you can have a continuous interpretation of this, continuous measurement interpretation of this stuff. And Howard Weissman is convinced of the opposite, and they from time to time they revive this discussion. And then, but in our case, it's very simple. So we're avoiding this discussion, and we are just saying the following. I mean, you prepare your system, and you just let it evolve with this equation, okay? And you're not monitoring. This equation is independent of what you do in the lab or not. But eventually, at all times, you can write the total state of your system like this. Of the whole stuff, yeah, at any time. So if at some time I go to the environment and I just project the state of the environment in this basis here, and I find out in which, I mean, a result that tells me in which coherent state it is, then I know the state of the system is this one. And this is just one-shot case. And actually, I didn't want to go into details there because then the results looks more complicated than that. That's what I was showing. Is actually you have to optimize these curves here for the time you want to measure. So it's not like in the Markovian case in which you can optimize for the whole time because you're measuring all the time. Here you want to have this, you want to have the optimal unraveling, let's say for time 3. And this means you select this parameter key from the beginning such that it is optimal for this time. If you now want to measure at time 2, it's probably that the parameter is different. And then to produce this stuff here, you will have to make measurements only at time 1, a set of measurements. Then at time 2, you do it again, and you produce this time by time in just one shot. Because the difference is that after you measure, you really destroy the whole dynamic. It's not like in the Markovian case that you can, it is organic into the system, into the theory that you're measuring all the time. Here is not. Thanks.
Other questions? Okay, so let's thank Carlos again.